This video is a continuation of 3.4. This is a small section in there about the Descartes rule of signs. Now, the description right here of the Descartes rule of signs says that if n is the number of sign changes in either p of x or p of negative x, then the number of positive or negative roots may equal to n minus 2, n minus 4, n minus 6, which is really a convoluted way to say what they're trying to say. Essentially, they're saying, if I look at f of x, and between each term, if it changes from negative to positive or positive to negative, we would count how many times that happens, and that tells us the n number of sign changes there were, which tells us the possible number of roots that are positive. So let's look at this example and let's figure this out. So if f of x equals x to the third plus 9x squared plus 4x plus 8, I look at this, it's positive term, positive term, positive term, positive term. There are 0 sign changes between the terms, and so there are 0 possible positive real zeros. Okay, so that's really helpful because if I use the rational zero theorem to figure out all the possible rational zeros and half of those are positive, I don't check with synthetic division any of those possibilities because that would waste my time. I know right here that there are no positive real roots. Okay, so then I'm going to check f of negative x. So f of negative x is going to be negative x to the third plus 9 times negative x squared plus 4 times negative x plus 8. And remember, if there's an odd power, then this is just the same as negative x cubed. This one's an even powered one, so negative x times negative x is going to be positive x, so I get positive 9 times positive x, so that's going to be positive 9x squared, minus 4x plus 8. So I can see I have negative to positive, that's 1 sign change, positive to negative, that's 2, negative to positive, that's 3. So there are 3 possible negative real zeros. Or, if I take that n value, so this is like my n value, and I subtract 2 from that, etc., 3 minus 2 is 1. So there's either 3 negative real zeros or 1 negative real zero. Remember, the rational zero theorem tells us that I can take the factors of the constant term and put them over the factors of the leading coefficient, and that gives me all the possibilities for possible real rational roots. So my factors of 8 are going to be your plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and the factors of 1, the leading coefficient is a 1, are going to be plus or minus 1. So we get all these possibilities. Remember this? Plus or minus 1 over plus or minus 1, plus or minus 2 over plus or minus 1, plus or minus 4 over plus or minus 1, plus or minus 8 over plus or minus 1, right? And then we can kind of look and see, okay, well, 1 over 1, that's going to give us plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. And then we can use synthetic division. The Descartes rule of signs tells me I do not need to check any of those positive ones. I don't need to do positive 1 or check positive 2 or check positive 4 or check positive 8. Don't use synthetic division to check those because there will be 0 positive real zeros. So what I might want to check would be negative 1, negative 2, negative 4, or negative 8. I hope that makes sense. I think it's really cool. Okay, so now we're going to put this all together. Okay, so this is stuff that we did from earlier in, not just in this section, but earlier in this chapter as well. we're going to use our knowledge of properties of polynomial functions to determine all zeros without a calculator. We're also going to determine some end behavior and other things that we've seen before. So, we're going to use our knowledge of properties of polynomial functions to determine all zeros without a calculator. For the function f of x equals negative 4x to the third plus 15x squared minus 8x minus 3. So first off, we're going to determine the end behavior of f of x. Now the degree is 3, so it's odd. The leading coefficient is negative because it's negative 4. So essentially we can think of a regular cubic, and remember it's going to be the reverse. So on the left, okay, it's going to rise, and on the right it's going to fall, okay, because we're looking at the opposite of a regular x cubed function. Now, we want to list all possible rational zeros, so we're going to take our factors of negative 3, which is going to be positive or negative 1, positive and negative 3, and those are going to be our numerators, the factors of the constant term, and then we're going to put those over the factors of the leading coefficient, which is negative 4. So the factors of that are going to be positive and negative 1, positive and negative 2, positive or negative 4. So we get positive or negative 1 over 1, okay, positive or negative 3 over positive or negative 1, positive or negative or negative 1 over 2, positive or negative 3 over 2, our fractions, our friends, our favorites, positive or negative 1 over positive or negative 4, positive or negative 3 over positive or negative 4. So we get a lot of options, right? If I simplify those down, I'm going to end up having positive or negative 1, positive or negative 3, positive or negative 1 half, positive or negative 3 halves, positive or negative 1/4, positive or negative 3/4 as my possible rational zeros. Okay? So then we're going to use the Descartes rule of signs to determine the possible number of positive and negative zeros of f of x. So first we look at f of x, and we see how many sign changes there are for f of x. I get 1, 2, because it goes from negative to positive, positive to negative, and then it goes negative to negative, so we don't count. So the number of possible positive real zeros are going to be 2, and remember, then we have to subtract by a factor of even numbers, so 2 and then 2 minus 2, which is 0. So there are either going to be 2 positive real zeros or they're going to be 0 positive real zeros. Okay, then for the possible number of negative real zeros, we need to look at f of negative x. So I'm going to do f of negative x, which is going to be 4x to the third. I'm kind of doing some of this work in my head, plus 15x squared plus 8x minus 3. Remember that when you do negative x to the third, it's still going to be a negative x to the third. It'll still be negative, but you multiply that by negative 4. So negative 4 times negative x to the third is going to be positive 4x to the third. The x squared is going to be positive, and then you have negative 8 times negative x, which gives you a positive x. Okay, so we actually only have one sign change because it's positive to positive, positive to positive, positive to negative. So there's only one sign change when I do f of negative x. So I'm going to use synthetic division to test for rational zeros. in one moment. So I've shifted this up. I made sure I still have my list of possible roots. I see that there might be 2 positive real roots, so I'm actually going to start with 1. I'm going to do my synthetic division. I bring down my first value, and I have -4. -4 times 1 is -4, and then I add these together. 15 plus -4 is 11. 11 times 1 is 11. Add those together, and I get positive 3. 3 times 1 is 3, and those cancel. Remember, when there's no remainder here, that means that 1 is a real root. So I know that I can separate that original polynomial into x minus 1, and then -4x squared, sorry for the space, plus 11x plus 3. Okay, now we can just use the quadratic formula on this to find the other rational roots. So Descartes' rule of signs is super helpful. It could save you a ton of work. I wouldn't want to go, if I knew on that previous problem that we had 0 positive roots, how much time would I waste if I tried +1, +2, +4, +8? I would have wasted so much time. So please make sure you use this rule accordingly, and it will help you out.